in MT 5504 mathematical programming. We are at the stage of big M method. We have seen previously one example. Now we are today starting the another example. First example was only having equality in the sign. Today we will start with the inequality in the sign. So let's start with the simple problem with the inequality. Problem is that maximize z is equals to 3x1 minus x2 subject to constraints 2x1 plus x2 is greater than or equals to 2. x1 plus 3x2 is less than or equals to 3 and x2 is less than or equals to 4. With of course x1 and x2 are non-negative. So previous case was having one sign with the equality. Now we are having a sign with the greater than or equals to type, and problem is of the maximizing form. So first of all we convert this in a standard form using all the previous methods, means introducing slack and surplus variables. So see the situation that here problem is maximize z. So maximize z is equals to 3x1 minus x2 subject to constraint. Here this quantity is higher than 2, so we have to remove positive quantity from here, means it is called surplus variable. So we will introduce surplus variable in the first constraint. So we are having 2x1 plus x2 minus s1 is equals to 2. Then in the second constraint it is already of the less than or equals to type. So we are having just x1 plus 3x2 plus s2 is equals to 3. In the third constraint also it is of the form less than or equals to type. So we will introduce x2 plus s3 is equals to 4. Here we are having x1, x2, s1, s2, s3 all are greater than or equals to 0. So this is standard form, okay, of given linear programming problem is this. So there is now no need to see this. Now we only focus on the standard form. From the standard form, if we want to get a initial basic feasible solution, in that case all we are used to do is take x1, x2 means initial variables be 0. If we keep this, then from the second constraint we are having s2 is equals to 3. From the third constraint we are having s3 is equals to 4. But from the first constraint we are having s1 is equals to minus 2. That is not satisfying the non-negativity of our variables. So to start the simplex method we require all variables non-negative, means we cannot continue with s1 is equals to minus 2. So as the previous cases, again we are having equality here, so we can introduce artificial variable. So to get the artificial variable we start with, so this is not our feasible solution, okay. This is not a feasible solution. So we start with the another form of this given linear programming problem as by introducing artificial variable. So after introducing artificial variable, we have the form like this, maximize z is equals to 3x1 minus x2 subject to constraint. In the first constraint only we have to introduce artificial variable. Okay, so there is 2x1 plus x2 minus s1 plus a is equals to 2. The second constraint is as it is, so it is x1 plus 3x2 plus s2 is equals to 3. Then third constraint is again same, so x2 plus s3 is equals to 4 with your x1, x2, s1, s2, s3 and a all are non-negative. Okay, since this is artificial variable and our objective is maximize z, the coefficient of and your introduced artificial variable a will be minus m in your objective function, and this m is too much large, as we have seen previously that m is more than 10 power 10 power 10 power 10 power 10 factorial 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 and so on. So you can think of a too much large number. Okay, and others coefficient means s1 s2 s3's coefficients are 0. Okay, if from this we want to identify initial basic feasible solution, so take x1, x2 and s1 0, so you will have a is equals to 2. From the second constraint you are having s2 is equals to 3 and as3 is equals to 4 from the third constraint. Okay, so using that we are making the initial table. So for the initial table we will have values of CB means coefficients, then basic variables, its value, then first variable, second variable, s1, s2, s3 and your artificial variable. Coefficients of them are respectively 3, minus 1, 0, 0, 0 and minus m from the objective function here. Okay, now in a basis we are having at the first stage artificial variable from the first constraint, this one. Then from the second constraint we are having s2's value, and from the third constraint we are having s3's value. Again their coefficients are here minus m, 0 and 0. Value of a is initially 2, value of s2 is initially 3, value of s3 is initially 4. Now write the coefficient table from simplex situation means constraints. So here it is 2, 1, then minus 1. Here these variables are not there in the first constraint, and this is 1. Then from the second constraint we are having 3, 1, first x1's coefficient is 1. Okay, so x1's coefficient is 1, then x2's coefficient is 3, then s1's coefficient is 0, s2's coefficient is 1, s3's coefficient is 0 and a is not there. Then from the third constraint we are having x1 is not in the third constraint, and x2 is 1, s1 s2 are 0 and s3's coefficient is 1, a is not there in the third constraint. So now we have to evaluate zj. So the value of zj is minus m times 2, so minus 2m, minus m times 1, so minus m, minus m times minus 1, so m, then minus 1 times 0, so 0, minus 1 times 0, so 0, minus 1 times 1 is minus m. So Cj minus Zj is 3 minus 2m, 3 minus 2m, so 3 plus 2m, minus 1 minus m, so minus 1 plus m, minus 0 minus m, so minus m, 0 minus 0, so 0, 0 minus 0, so 0, and minus m minus m, so 0. And as you have noticed or not, I don't know, but whenever whichever variable is in basis, corresponding Cj minus Zj's are always 0. Okay, so even if variables are in basis, if you will not calculate Cj minus Zj, then already its coefficient will be 0. Cj minus Zj will be 0. Okay, now what is the maximum value from this? So here it is 2m and here it is 1m. So m is too much large. So this 2m is again too much larger than m. So this quantity will be larger than anyone else here appearing. So maximum value for Cj minus Zj is for x1. So we will introduce x1 in our basis. So now we have to evaluate ratio, replacement ratio. So for the replacement ratio, we are taking ratio of 2 here and 2 here. So 2 by 2 is 1, 3 here and 1 here, so 3, and 4 here and 0 here, so it is infinite. So minimum from the replacement ratio is for the variable a, means your a artificial variable will be removed from basis and x1 will enter a basis. So we have to make this quantity 1, the other quantities from the same column must be made 0, means this and this must be made 0. Okay, so to do that we will apply RRE process. So to get that, let's start again new table. So first of all we will make a table x1, x2, s1, s2, s3, a, their coefficients. So 3, minus 1, 0, 0, 0. Here now a is removed from basis and we don't want artificial variable anymore. So we will not calculate even Cj minus Zj or anything for a. So we will not write a table for a. Now here it is xb, b and cb. In basis now a is replaced by x1. So here it will be x1, then s2, and then s3, and x1's coefficient is 3, s2's coefficient is 0, and s3's coefficient is 0. Value here now we have to make 1. So to make 1 we have to divide this by 2. So dividing by 2 we are having 1, 1 by 2, minus 1 by 2, 0, 0. We are not calculating for a, so it will be not there. Now to make this entry 0, it is already 0, so there is no need to apply RRE process for the third row. So we are just writing itself. So 4, 0, 1, 0, 0, 1. And to make this entry 0, all we have to do is subtract from this row, we will subtract this row. So 3 minus 1, so it is 2, 1 minus 1 is 0, 3 minus half is 2 and half, that is 5 by 2, 0 minus half. So 0 minus half is half. 0 minus half, it is half. 1 minus 0 is 1, and here it is 0. Okay, so this is your second table, applying first ternary process. Now evaluate Zj. So to evaluate Zj, again you know that multiply 3 with 1, so 3 times 1 is 3, 3 times half is 3 by 2, 3 times minus half is minus 3 by 2, 0 and 0. So Cj minus Zj is 3 minus 3 is 0, minus 1 minus 3 by 2. So minus 1 minus 3 by 2. So it is minus 5 by 2. Then here it is 0 minus 3 by 2. So it is 3 by 2. Here it is 0, 0, 0 minus 0 is 0. So we are having Cj minus Zj in this way, and positive value is only for S1. So S1 will enter a basis. Now we have to evaluate which variable will leave a basis. So for that we have to evaluate replacement ratio. So here we have to divide minus 1 by minus 1 by 2, but that is a negative quantity. So infinite, 2 by 1 by 2, that is 4, and 4 by 0 is again infinite. So only positive quantity means non-negative quantity is 4. So the corresponding variable S2 will leave a basis and S1 will enter a basis. Okay. So as previously we have done, we have to make this entry 1 and this entry 0. Okay. So again in the third constraint we are not required to do any process because this entry is already 0. So let's make a table, next table. We are having x1, x2, s1, s2, s3, xb, b, cb. In basis now we are having x1, s2 is now replaced by s1, so x1, then x2 is replaced by s1, and s3 it's as it is. Coefficients are 3, minus 1, 0, 0, 0. x1's coefficient is 3, s1's coefficient is 0, s3's coefficient is 0. Now to make this entry 1 we have to multiply by 2. So multiplying that by 2, so we are having here value 4, here it is 0, 2 and half, that is 5 by 2. So multiply by 2 is 5, here it is 1, here it is 2, and this is 0. And here entry is already 0, so all we have to write itself. So 4, 0, 1, 0, 0, 1. And to make this entry 0, we will just add these two rows. So directly we will get that 0 entry. So adding that two rows, we are having values 3, then 1 plus 0 is 1, 5 by 2 plus 1 by 2, 2 and half plus half, so it is 3. Here it is 0, here it will be 1, and here it is 0. Okay. Now we have to start evaluating Cj minus Zj. So first of all evaluate Zj. So 3 times 1 it is 3, 3 times 3 it is 9, then 3 times 0, so it is 0, 3 times 1 is 3, and 3 times 0 is 0. Cj minus Zj, so 3 minus 3 is now 0, 1 minus 9 is minus 10, 0 minus 0 is 0, 0 minus 3 is minus 3, and 0 minus 0 is 0. So all quantities of Cj minus Zj are less than or equals to 0. So we are reached to the optimal solution. So what is the optimal solution? So optimal solution is for x1 is equals to 3, x2 is equals to 0, and your objective function was z is equals to 3x1 minus x2 is 3 times 3 minus 0, that is 9. So our objective function is maximized with given constraints at x1 is equals to 3, x2 is equals to 0 with value of z is equals to 9. Okay. So we have seen today that whenever we are having constraints with the greater than or equals to type, we are not means after converting it to the standard form, we are reaching to the situation with minus s1 is equals to some positive quantity. So at the end we are having S1 is that negative quantity, and we are not able to start the simplex method. Okay, so to start the simplex method, all we have to do is introduce artificial variable, make its coefficient in your objective function to be the large minus m. You can put insert value of m if you want, but better to write m itself, and then getting the initial solution with considering that corresponding as your variable 0 like this, and your artificial variable's value is from the constraint, and start the simplex method. Also, when we remove our artificial variable from the basis, then we are removing corresponding value in our objective function also, and the corresponding full column will be removed, means no further we will not calculate the corresponding values of a in any of the constraints, and we are ending with the solution. Why it is so? Because its coefficient in objective function is too much large m. So again it is not going to give you any contribution to the optimizing our solution, means giving maximum profit, because see, as whenever you will have any quantity from this now in onwards, so something times whatever value is here, then you will have Cj minus Zj, then Zj is any real number, and means finite number, and Cj is too much large m with minus sign. So this quantity will be too much large. Okay, so we will not calculate, that is why we are not calculating for the artificial variable further, and hence we are, after applying whatever simplex process is required, we are ending at the optimal solution. Okay, so this is how we can deal with the problems with the greater than or equals to type constraints with the positive quantity at the right hand side. I am giving you problem to calculate your own, so you can see how to work with this type of problems. So exercise. Let your objective function is 2x plus 2y plus 4z, and you are supposed to maximize these. Oh, sorry. you are supposed to minimize this. Minimize this subject to constraints 2x plus 3y plus 5z greater than or equals to 2, 3x plus y plus 7z less than or equals to 3, x plus 4y plus 6z less than or equals to 5, with your variables x, y, z are greater than or equals to 0, and you are supposed to solve this linear programming problem by your own. See, as we have seen that whenever problem is of the minimizing situation, then we are used to do is convert minimizing problem in the maximizing form. So first of all, your problem will be converted like this. This maximize z is equals to minus 2x minus 2y minus 4z. Then subject to constraints 2x plus 3y plus 5z is greater than or equals to 2, 3x plus y plus 7z less than or equals to 3, x plus 4y plus 6z is less than or equals to 5, and your x, y, z are greater than or equals to 0. So this is known situation to you, and solve this as we have done previously. And I am writing means whenever you are getting value of x, y, z at the last table, insert this values in your original. This is your z star, okay, not original function z. So whenever you are finding value of z, you have to put these values of x, y, z in our original objective function, means this one. So I am hoping that you will solve this. I am writing the answer at optimal solutions for this is x is equals to 0, y is equals to 2 by 3, z is equals to 0, and capital Z's value is 4 by 3. Okay, so verify that you are getting the same solution. So for till the next day, stay at home and stay safe. Thank you.